Now a four-stroke engine does intake, compression, combustion, and exhaust. This is what most are familiar with nowadays, and it is the concept behind the engines in most vehicles on the road today. Now an Atkinson and a Miller cycle engine, they also do intake, compression, combustion, and exhaust. However, they differ in a small but very important detail which allows them to be significantly more efficient than an Otto cycle engine. And in today's video, we'll dive back into the history of engines to learn about their evolution, as well as the birth of and the difference between Otto, Atkinson, and Miller engines. Now, the four-stroke or Otto engine as we know it today was invented in 1876 by German Nicolaus August Otto. Now, this statement is a oversimplification because it makes it sound as if Mr. Otto sat down one evening, and after some good hard thinking, he came up with the revolutionary concept of the four-stroke engine. The reality is that the birth of the four-stroke engine was actually preceded by a very thorny path full of difficulties, risks, experimentation, and failure. And also attributing the invention of the four-stroke engine to a single individual is a bit unfair because although Mr. Otto is the key person behind the project, he received a lot of help and support from many of his friends and colleagues. Now, before becoming involved with engines, Mr. Otto was actually a salesman. He sold merchandise to grocery stores around the city of Köln or Cologne in Germany. But even as a child, he demonstrated great passion for science and technology, and although he never received formal engineering or other higher education, his intelligence, creativity, and passion more than made up for this and became the engine behind his engines. In 1860, during his travels as a salesman, Otto ran into the Lenoir engine. This was an atmospheric engine developed by Belgian-French Jean-Joseph Etienne Lenoir. It ran on a mixture of coal gas and air and was only 4% efficient. It managed to squeeze only 2 horsepower out of 18 liters of displacement, but these were the very beginnings, the first baby steps of internal combustion, and this engine should still be considered a success because it was the first ever internal combustion engine to be commercialized. Several hundred Lenoir engines were made and sold both in Paris and in London. But right after seeing it, Otto believed that the Lenoir engine could be substantially improved. And just a year later, in 1861, he had built his very own personal replica of the Lenoir engine for experimentation purposes. And very soon he made a critical discovery. The Lenoir engine would ignite the air-fuel mixture right after ingesting it. In other words, there was no compression stroke. Otto discovered that if the air-fuel mixture was compressed before being ignited, the resulting combustion was much better. It was stronger and it burned more evenly. It also generated enough power to turn the crankshaft many times over after just a single such combustion event. Of course, Otto attempted to build such an engine, but ultimately he failed because all of his prototypes would self-destruct after running for just a few minutes. After 3 years of experimenting with different prototypes, Otto had spent all of his own money as well as all the money he borrowed from friends, and all he had to show for it was a graveyard of engines. So in 1864 he realized he couldn't do this alone, and he joined forces with wealthy industrialist Eugen Langen, and he founded the first ever internal combustion engine manufacturing company, together with Gottlieb Daimler as the technical director and Wilhelm Maybach as head of engine design. The company was headquartered in the German town of Deutz. It's interesting to note how all the people who were present and key in the first ever internal combustion company would also become key persons in future combustion-centered companies that would eventually grow into global industrial giants with widely recognized branding. In the same year that Otto and Langen founded their company, they also created a much improved version of an atmospheric engine. It was 12% efficient and made half a horsepower. As it was dramatically more efficient than anything else at the time, it also won the gold medal at the Paris World Fair in 1867. The design of the engine is actually very interesting because it uses a free-floating upside-down piston that is attached to a toothed rack. When we say free-floating piston, what we mean is that there's no connecting rod or crankshaft or anything else connected to the piston that is limiting the motion of the piston. Essentially, the engine works like this. Our upside-down piston and rack sit inside a long, upright vertical tube. A system of gears lifts up the piston slightly, which opens a slide valve and allows air and fuel in. The fuel was actually lighting gas. Right after the fuel and air come in, a port opens and exposes the air-fuel mixture to an open flame, which then of course ignites the air-fuel mixture and sends the piston flying upward. As the piston goes up, the rack of the piston then rotates a gear, which was essentially a one-way clutch. What this means is that it can only rotate in one direction, but it freewheels in the other direction. And this gear is then connected to the output shaft of the engine. And then you could connect a belt to the output shaft and use it to perform some type of work. What prevents the piston from bursting out of the engine is nothing other than air pressure. There is air trapped behind the piston, and as the piston goes up, it compresses that air until eventually it can't compress it any further. The air acts like a cushion that prevents the piston from hitting the end of the cylinder. As the piston sinks back down, the exhaust port opens and lets the exhaust gases out. The Otto Langen engine was made in power outputs from 0.5 horsepower up to 3 horsepower, and a total of 2,649 units were made and sold. However, the engine had a major drawback. The most demanded and most powerful 3 horsepower version actually needed 4 meters of headroom to operate due to the engine's tall vertical structure. However, the company failed to continue progress because of a disagreement between Otto and Gottlieb Daimler. Otto wanted to abandon atmospheric engines and once again try to develop a compression charge engine, an engine that compresses the air-fuel mixture before igniting it. That was his original idea. But Gottlieb Daimler refused, and he wanted to continue development of the atmospheric engine. Now, after they failed to come to an agreement, they finally went their separate ways. Otto again started work on a compression charge engine, whereas Gottlieb eventually started his own business. And in 1876, Otto's dream became reality. The very first true Otto cycle, the very first compression charge 4-stroke engine saw the light of day in this year. But Otto didn't do it alone. The engine was made possible thanks to contributions from Franz Rinks and Hermann Schumm, employees who were originally brought into the company by Gottlieb Daimler. This is why the very first Otto cycle engine is in some circles known as the Rinks-Schumm engine. Although it may not seem that way upon first glance, this engine actually has many of the elements that we can see on any modern engine today. There's a crankshaft, a connecting rod, there's even a camshaft. Inside we have a piston and some valves, and the engine does intake, compression, combustion, and exhaust. A figure that best exemplifies just how revolutionary the concept of a compressed charge 4-stroke engine is that in the 15 years prior to the development of this engine, the worldwide record for engine power output never exceeded 3 horsepower. In just a few short years after this engine was developed, the global power output record started dramatically increasing and quickly reached 1,000 horsepower. As you might expect, this engine was an instant commercial success, and of course Otto patented his design. Now the patent, is what brings us to Mr. James Atkinson, who, like many of his contemporaries, after seeing the commercial success of the Otto engine, started developing his own engine. However, there was a catch, and the catch was that for the engine to be commercially viable, it had to be different enough from Otto's design in order to not infringe on the patent rights. Now, Atkinson decided that the compression stroke, or that which allows the Otto engine to make more power, is something that could be improved upon. And this was to be done by reducing the length of the compression stroke in relation to the combustion or the expansion or the power stroke, as some call it. The idea behind this is that the engine spends more time harnessing the energy of combustion rather than wasting that energy on compressing the air-fuel mixture. Now, the logic behind this is sound because the air-fuel mixture definitely offers a significant resistance to compression. Remember how the Otto Langen engine used this property of air, the resistance to compression, to turn that air into a cushion for the piston. Now, the Otto engine takes a completely different approach. Instead of allowing the air to push the piston back down the cylinder, instead it uses the crankshaft and the connecting rod to essentially force the piston against the air-fuel mixture until that air-fuel mixture is compressed to a sufficient degree for optimal combustion. Of course, forcing the piston to essentially fight the air-fuel mixture wastes some of the energy created by combustion, leading to reduced efficiency. But by 1887, Atkinson made his concept into reality by creating this, the Atkinson cycle engine, an innovative design which allows the piston to complete 4 strokes during just 1 revolution of the crankshaft. If you observe the piston together with the crankshaft, you can see that we complete intake, compression, combustion, and exhaust, while the crankshaft makes just 1 revolution. Of course, the reason why that is possible is because of the additional arrangement of connecting rods on the engine. Instead of connecting the crankshaft directly with the piston via a single connecting rod, the piston rod, seen in blue, is instead connected to an intermediary linkage. As you can see, the piston rod never completes a full revolution. Instead, it only swings out left and right from the piston center line. Now, the trick to this engine lies in this simple fact. The length of the crankshaft and the main rod stack up in this position, whereas in this position their lengths do not add up and instead simply equal the length of the main rod. This means that in this position the intermediary link gets pushed out of the center line and the piston pulled out of the cylinder a greater distance, whereas in this position that distance is reduced. The ultimate result is that the compression stroke is shorter than the power stroke. Now, Atkinson managed to patent his design, and the engine was manufactured and sold for a few years by the British engine company. Atkinson even managed to license the design to other manufacturers. The engines demonstrated impressive efficiency, and the power output ranges of the engines made and sold ranged from a few horsepower up to 100 horsepower. So, if Atkinson managed to improve efficiency, then you must be asking yourself, why don't we all then have Atkinson cycle engines in our cars today instead of Otto cycle engines? Well, the answer to that is pretty simple, and it's that the logic of trying to reduce the compression stroke is a bit flawed. A compression stroke may sap some of the engine's power, but the gains it creates more than make up for it. Saying that the compression stroke consumes power is the same as saying that a supercharger consumes engine power. Yes, it does, but the benefits it creates are far greater than the price paid for it. A car engine is more powerful with a supercharger than without it. This is why the most powerful engines in the world all have giant superchargers and are all Otto engines. The Atkinson engine may be more efficient than the Otto cycle engine, but the price it pays for this is power. If you reduce the length of the compression stroke, then you also reduce the amount of energy packed into the combustion stroke that follows. An Atkinson engine is simply much less powerful and less responsive than an Otto cycle engine. And this is especially important in non-stationary engines inside vehicles where power demand transitions constantly occur. So yes, efficiency is important, but power and responsiveness are too. Another reason why Atkinson's design never took off is that the complicated set of rods and linkages made the engine expensive to manufacture and maintain. It was also extremely difficult to balance all of this, making the engine unsuitable for high-speed operation. The final nail in the coffin of this design is that Otto lost his patent for the compressed charge 4-stroke engine in 1886. He lost it because he couldn't prove that his design is sufficiently different from a prior design of Frenchman Alphonse Beu de Rochas, or Rochas, I'm not sure. Rochas never tried to build his engine, but his patent was essentially the same as that of Otto. So with Otto's patent gone, everyone abandoned making further investments into novel designs and instead focused on manufacturing an already proven design from Nicolaus Otto. By 1889, more than 50 companies in several different countries were manufacturing Otto cycle engines. In fact, this is what we did for the next 60-something years. We focused on improving an existing design, a design that ultimately demonstrated incredible potential and changed our world, but the concept of reducing the compression stroke with the goal of increasing efficiency lay dormant all the way up until 1957. In this year, US engineer Ralph Miller patented the Miller cycle. Now, the concept behind the Miller cycle is exactly the same as the concept behind the Atkinson cycle, and it is to reduce the power sapping effects of the compression stroke. The big deal is that Ralph Miller chose a much more effective, a much simpler and more elegant solution to achieve his goal compared to the complicated set of rods and linkages from Atkinson's design. And the solution is this. Keep the intake valve open longer. That's it. The construction of the engine stays absolutely the same as that of a conventional Otto engine. The only thing that differs is the valve timing. We of course open the intake valve during the intake stroke to allow the air-fuel mixture into the cylinder. A conventional Otto engine closes the intake valve before the compression stroke begins. This is done in order to ensure that the entire length of the cylinder is used to store and compress the air-fuel mixture, leading to optimal power output. The Miller engine too, of course, opens the intake valve during the intake stroke, but it differs from the Otto engine in that it doesn't close the intake valve when the compression stroke begins. The intake valve is kept open during the first 20 to 30% of the compression stroke. An open intake valve, of course, means that the upward motion of the piston simply pushes some of the air-fuel mixture back into the intake manifold. The piston can't compress anything until the intake valve closes. In other words, the compression stroke can't begin before the intake valve closes. The compression stroke doesn't begin here. It begins here, because this is when the intake valve closes. The end result, a compression stroke that is shorter than the power stroke, but without all the linkages. Efficiency is improved because for 20 to 30% of the cylinder's length, the piston isn't wasting the engine's energy on compressing the air-fuel mixture. Okay, this is nice, a much more simple and elegant solution, but I know what you're thinking again, and you're thinking that this is still useless because we still have reduced power and responsiveness compared to a regular Otto cycle engine, and nobody wants a Miller engine in their car. Well, actually no, because there's another very important aspect to Miller's prototype, and this is because Miller designed his engine in the late 50s, which means that at his disposal he had something that Atkinson did not, a technology that was well matured by the late 50s, and that technology is superchargers. Miller added a supercharger to his engine in order to make up for the loss of power and responsiveness compared to the Otto cycle. As you probably know, a supercharger is a forced induction device. What this means is that a supercharger essentially compresses the air and then stuffs that air into the engine. This means that it's doing some of the work that the engine actually does during the compression stroke. So in a Miller cycle, when we have the intake valve open during the compression stroke, when the engine actually pushes some of the air-fuel mixture out of the cylinder, there is still enough air-fuel mixture remaining in it to make for a decent combustion because the supercharger had already stuffed the cylinder full of compressed air just milliseconds before. And a supercharger is a great fit for a Miller cycle engine because it increases power and torque and responsiveness at very low RPM and offers near instant response, unlike a turbocharger which has a bit of a lag. In fact, in the late 90s, Mazda put Miller's concept into practice with the kj-zem engine, which they installed in the Mazda Millennia /Shadows 9 /Unos 800. It's the same car, it just had a different name for different markets. It was a 2.3-liter V6 running the Miller cycle. Interestingly enough, it didn't have a Roots type supercharger, which is usually what's recommended for a Miller cycle engine because a Roots type supercharger is very small and offers the most benefits at very low RPM, where the lack of responsiveness of a Miller / Atkinson cycle is felt most painfully. Instead, the Mazda Millennia had a twin screw supercharger, which gave it a very interesting, almost like a modern supercharged muscle car sound. The kj-zem managed to output 217 horsepower and 285 newton-meters of torque. This was 47 horsepower more than Mazda's regular naturally aspirated 2.5-liter V6. Impressively enough, despite being supercharged, it was still more efficient than the naturally aspirated V6. On paper, it was about 20% more efficient. However, in practice, most users did not report that sort of efficiency, probably because a supercharger has to sap some of the engine's energy in order to operate, because it is operated usually by the crankshaft connected via a belt, so it consumes engine energy and reduces efficiency. But that wasn't the problem with the kj-zem engine. It was an impressive engine, impressive power, impressive efficiency. The real problem was that the Mazda Millennia with this engine was dramatically more expensive than a Millennia with a regular 2.5 liter V6, making the car a sales failure, and it was discontinued after just a very brief period on the market. But just as the Mazda Millennia was about to die, Toyota revived the concept behind the Atkinson cycle. They did it in 1997 with the first generation of the Prius and its 1NZF-xe engine. But this time, instead of a supercharger, we have an electric motor. Now, as we know, electric motors produce instant torque and they don't sap the energy of the engine like superchargers do. This means that electric motors and Atkinson cycle engines are a match made in heaven, and this was put into practice in all of Toyota's hybrid vehicles. Another important benefit that modern technology has brought to Atkinson and Miller cycle engines is VVT, or variable valve timing. This enables the engine to run an Atkinson cycle during reduced load conditions, such as, for example, highway cruising, but at high RPM when the driver demands maximum power output, the engine can revert back into regular auto cycle for reduced efficiency but increased power output. However, variable valve timing can only increase peak power output at high RPM. It can still not fix reduced responsiveness at low RPM. For this, we still need an electric motor or a supercharger to provide the kind of responsiveness and torque you would expect from a modern engine at low RPM. Although Toyota's usage of the Atkinson cycle remains the most popular to date, Mazda has not abandoned the concept. They have revived it yet again in a fashion very similar to what we have seen in the Mazda Millennia. This time it's called skyactiv-x, and in addition to a small Roots-type supercharger and the Miller cycle, we also have the first ever commercially available engine capable of running spark-controlled compression ignition, a gasoline engine capable of diesel-like combustion with extremely lean air-fuel ratios, which makes it probably the most efficient non-hybrid gasoline drivetrain available today. The final point I want to make has to do with naming conventions. As you can see, Toyota uses Atkinson, Mazda calls it Miller. In general, the consensus seems to be that if there's a supercharger, then it's a Miller cycle engine. However, in reality, it's a bit irrelevant because the concept behind both of these engines is the same, and it is to reduce the amount of energy wasted during the compression stroke in order to improve efficiency. Atkinson did it with rods and linkages, Miller did it with valves, Toyota did it with valves, Mazda too, everybody else, all the modern engines are done with valve timing, so technically Miller cycle would be the more appropriate name, but again, neither naming convention is wrong because the concept behind both of these engines is the same, and it is kind of interchangeable. So yeah, there you have it. That's pretty much it. A bit of theory and a bit of history on Otto, Atkinson, and Miller. As always, thanks all for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.